algebra students. Mr. Lawrence here with your next flipped lesson. And we're continuing our exploration of patterns. Now, yesterday's patterns were all what we call linear. And I'll show you why they are linear. If you hear the word linear, some of you are going to go, what does that mean? But stop and think about it. Write down the word linear. Okay, linear. Okay, the root of linear is not ear. It's line. If you were to graph these, make a table using the graphing method that we talked about in the last unit, put in values and get values out. If you had a pattern of, like, say, 2n plus 1 or something like that, maybe you said, well, y equals, you could change the n to an x, and you made your little table and you plugged in values for x and y, and what would happen is the points you plot would all create a line. And so we call that a linear pattern. Now, we're going to be able to tell if it's linear or not without actually graphing it, because it's really simple to do. But I'm going to do this one, and we'll see if you can tell why it's linear. All right, remember that I'm going to first plug in these numbers, the 7, 11, 15, 19, right? So 7, 11, 15, 19, and 23. Okay, now I start looking for the first differences, right? Because I want to find the nth term. If I can find the nth term, then finding any other terms will be super duper simple. So I'm going to find this, and that's what, plus 4 and plus 4. And look at that, it's repeating every single time. It's plus 4 all the way. Oops. All right, so that means my pattern has to be something like 4 times n, or more simply said, 4n. So now I'll take these numbers here, 1, 2, 3, 4, and 5, and I'll stick them in for n into this formula. And I'll write them below the 1, 2, 3, 4, and 5. So 1 times 4 is 4, then we get 8, and then we get 12, and 16, and 20. And now I'm going to compare up. I'm going to ask myself, what do I do to turn 4 into 7? Well, I add 3. Let me change colors on that. Add 3. Okay, 8 to 11, sure enough, add 3. 12 to 15, add 3. It looks like I add 3 every single time. Okay, that means my answer must be 4n plus 3. Okay, so now that I know it's 4n plus 3, I can do 20. Okay, so I substitute 20 in for n, so, I'll show the work down here. That'll be 4 times 20, and then plus 3, and that'll end up being 83. Okay, and then to do this one, be 4 times 150, which is 600, plus 3, so it'll be 603. If you're wondering how I did that so quick in my head, well, I know that 15 and 15 is 30, and then another 30 would be 60. Well, this is 150, so it wouldn't be 60, it'd be 600. Okay, you can do things really quick. I wouldn't do the long way of multiplication. All right, so our answer was this 4n plus 3 guy. I'm going to write that over here. And I'm going to tell you that he's linear. It's a linear pattern. He generates a linear pattern. I'm also going to tell you that this is linear and this one here is linear. Okay, this is also linear. These are all linear patterns. Okay, I could have 2 negatives, it would still be linear. Just like that. All right, now I'm not going to tell you why it's linear yet. We're going to look at the next pattern, and you should be able to tell me, because this next one is not going to be linear. Oh no, my sequence of numbers is missing. Let me go find it. Look at that, I found it. It was right there in my pocket. All right, first thing I'm going to do is I'm going to copy down those numbers into my table. So I've got 1, 4, 9, 16, and 25. Go looking for my first differences, right? So I'm going to get what? Plus 3, plus 5. Ooh, that's weird. plus 7 plus 9. Hey, they don't match. My first differences don't match. Okay. Well, let's see here. Let's go for our second differences then. All right, so let's go find our second differences. Let's see what happens if I go down. If I find the differences of the differences. That's what the second differences are. Looks like from 3 to 5 is plus 2, and 5 to 7 is plus 2, and from 7 to 9 is plus 2. Ooh, those do match. I'm getting the same constant over and over and over again, namely plus 2. Whenever you get the same difference on your second differences, your formula is going to be something like n to the second power. Okay, n squared. It's not going to be a 2n. 2n would be like 1, 3, 5, 7, 9, where the first differences are all 2 apart. Our first differences were all different. Our second differences were all the same. So since we're on the second level down, we're going to use an exponent of 2. Hey, does that mean that on this previous one here, that we had an exponent of 1? Like, would it be okay if I snuck a little 1 on that? Yeah, it would be okay to do that. We don't write that 1 because we assume it to be there. Mathematicians are lazy. They like to do things as simple as possible. And I think you'd all agree it is more simple to write 4n plus 3 instead of 4n to the first power plus 3. It may not seem like a big deal, but when you're doing a very large equation or solving a proof or something, that could get pretty tedious adding that in. So on the first level, we have the first power. On the second level, we have the second power. All right, so we're going to generate the sequence. We're going to plug in these numbers, the 1, 2, 3, 4, and 5, in for n in the formula of n squared, and we'll see what we get. And if they match perfectly, we'll have our answer, and if they're off by a little bit, we'll have to adjust them. All right, so 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Look at that, it matches perfectly, doesn't it? Yeah, I don't have to do anything to turn 1 into 1, or 4 into 4, or 9 into 9. So my formula is n to the second power, or n squared. To do 200 squared, well, 2 times 2 is 4. It's 20 times 20, there's 2 zeros there, it's 400. 15 times 15 is 225, and then there will be 2 more zeros, so it'll be 22,500. By the way, the formula here is n squared, and this is not linear, this is quadratic. This is a quadratic. And I know some of you are so sharp, you've already figured out all of these linear ones, their highest exponent is 1, right? But on this one, the exponent is a 2. That's what makes it quadratic, because the exponent is a 2. All right, let's try another example. Say we have the pattern -2, 1, 6, 13, 22, on forever. Looks like I forgot a comma there. Again, I'm going to copy them into my table over here. Okay. And go find my first differences. It looks like I've got plus 3, plus 5, plus 7, plus 9. Oh, it looks very familiar. I'm going to get plus 2, plus 2, plus 2. The second differences are all the same. By the way, if it's an n squared formula, you'll always get plus 2 on the second difference. Okay, so I'm going to use n squared, and I'm going to work smart, not hard. I'm not going to do a lot of thinking. I know I just generated this pattern on the last problem, so I'm just going to copy it from memory. These don't exactly match, so I'm going to ask myself, what do I do to these red numbers to turn them into the black numbers, the original numbers? Well, it looks like on this last one, I have to subtract 3. On 16, I have to subtract 3. 9, I have to subtract 3. Looks like I'm subtracting 3 every time. So my formula will be n squared, take away 3. I can look up here to problem number 2 and see that 20 ended up being 400. Well, for n squared minus 3, it's going to be 20 squared minus 3. which will be 397. Okay, the 150 ended up being 22,500. Well, if I take 3 away from that, that'll end up being 22,497. And there you go. And so our formula was n squared minus 3. And again, that is quadratic. Quadratic. Right, because the exponent is 2. Okay, the highest exponent. All right, I'm going to give you one to try on your own. Looks just like that. 6, 9, 14, 21, 30. Hike. And it keeps on going forever. You go ahead and see if you can figure it out on your own. Unpause the video when you're ready to see my solution. All right, here comes my solution. So if you're not ready, pause the video. But if you are, that's fine. Oops. 14, 21, 30. Okay, first differences. Second difference is, looks like it's an n squared. All right, n squared. And I know it looks like 1, 4, 9, 16, 25. Looks like I'm adding 5 each time. Yeah. So plus 5, plus 5, plus 5. So we're going to get an n squared plus 5. All right, well, 20 squared is 400 plus 5, 405. This will be 22,505. And there you go, piece of cake. All right, Mr. Lawrence signing off. There will be an extra practice video if you need a little bit of help. All right, and we'll get a little more practice with this in class tomorrow. So remember that when the formula looks like the first one, where it's something like 4n plus 1, that is a linear pattern because the highest exponent is 1. When the pattern looks like this, n squared plus 5, that is a quadratic. That's what we call it. That's because the exponent is a 2. All right. Have a good night, everybody. Good do.